Good morning, students. Today's topic is Prim's algorithm under design and analysis of algorithm. So, Prim's algorithm is a famous greedy technique. It is used for finding the minimum spanning tree of a given graph. Before going into this, we need to know a term called spanning tree. So, spanning tree is nothing but it is a subgraph of an undirected connected graph. This MST is also a kind of tree in which the sum of weight of edge is as minimum as possible for the given graph. So to apply a Prim's algorithm, the input that is the given graph must be a weighted graph, connected graph, and it must be of undirected graph. These three conditions should satisfy while giving an input to Prim's algorithm. That is, the graph must be of weighted, connected, and undirected. The example is if we have three edges, that is undirected graph and it is connected graph and it should have some weight like from here 7 10. So this is an input for Prim's algorithm. So while implementing Prim's algorithm, there are some steps to be followed. The first one is step 1. We have to randomly choose any vertex from the given graph. For example, we have 1, 2, 3, and 4. It is of connected and also weighted graph like 8, and we can choose any vertex. For example, we can choose 1 or either 4 or either 2. Any vertex we can choose. Next one is the vertex containing to the edge having least edge is usually selected. Then next step 2 is find all the edges that connect the tree to any vertices. Then find the least weight edge, that is the least weight edge among those edges and include it in the existing tree. If including that edge creates a cycle, then we have to reject that edge and look for the next least weight edge. If it doesn't form a cycle, we can include it. Then next step 3 is we have to keep repeating this step 3 until all the vertices are included in the graph to obtain a minimum span. This is a simple implementation step for Prim's algorithm. So this is a complete algorithm. Then first step is we have start tree as a null, then u as 1. While this u is not equal to our vertices, then let u comma v be the lowest cost edge such that u belongs to u and vertices belongs to v minus u. Then tree, we have to include the tree. That weight you should include. For example, we have vertex. If t is equal to t union u comma v. If we add 8 here and the ridge, consider another ridge here as 9. Here 9, this is 3. First we can take 3 minimum, we can add. Next is 8, we can add. Next here we have 7, this smaller one. If we add this edge, it will form cycle, so we should not include it. That is T union U comma V. If we add this, it doesn't form cycle, we can add this in tree. Then U is equal to U union of then this vertex. If it doesn't form a cycle, we can add or else we can reject it. So consider this is an example for Prim's algorithm. We have 7 vertices here and some weight is there and it is connected. So it is connected, weighted and undirected vertices. So see, the above discussed steps are followed to find the minimum cost spanning tree in Prim's algorithm. So first, in this example, I see take 1 comma 6, 10 is minimum, so we can choose 10. In the next step, 25, that is while connecting 6 to 5, 25 is minimum. We can take 6. For example, take a graph as A, B, C, D, F, and E. Okay. So the weights are, you can take a simple example, 3, 1, 6, 5, this and this both are 4. We are connecting, here we have 5, here we have 6, here we have 2, here we have 8. So look at this. Let me take A as a starting vertex. So just draw vertices alone, sorry, edges alone. A, B, C, and D, and E, and F. Okay. So in this example, from A we have path from A to B, A to C, A to B, A to F, and A to E also we have path. But smallest one is A to B. So we should take as A to B as 3. So next node is we have to take. So A is now done. So now we have done with A. Next is smallest B. From B, what are the path we have? B to C, B to F. B to A is already visited. So B to F and B to C. So in this B to C smallest, so we have 1. So B to C we have 1. Next, so now B is also done. We next is C. From C we have path C to F, C to T, and C to B is already visited. So C to F we have 4. So C to F we have 4. So C is also visited. Next we have to take F. From F we have B already visited, A already visited, C is already a visitor, and E we have 2. So E to F is 2. Next one is E. From E, we have path from F, D, and A. This two was already visited. So E to D, sorry, F to D is we have 5. So this is the answer for this problem. To find the minimum cost, we have to add all these values, 3 plus 2 plus 4 plus 5 plus 2. So all together we get 15. The answer. So the logic behind this is we have to take any one as starting vertex, and from that vertex we have to find the remaining vertices, that is which is flowing towards it, and take the smallest among them, and from the smallest we should travel to the remaining vertex. If it is smaller than before value, we can replace, or else we should not replace that. So in this example, this is the answer given for that example. So the value is 1 to 6 is 10, and 6 to 5 is 25, and 5 to 4 is 22. Then 3 to 4 we have 12, and 2 to 3 16, and 14. So we have got the answer as 99. So this is the time complexity analysis of Prim's algorithm. If adjacency list is used to represent the graph, if adjacency list is used to represent the graph, then using BFS, we can find the time complexity. That is, all the vertices can be traversed in vertices plus edge time. So we have to calculate both the vertices and edge. So all the vertices are traversed in order of V plus E time. We traverse all the vertices of the graph using BFS and use a min heap for sorting the vertices, not yet included in the minimum spanning tree. So to get the minimum weight, we should use only min heap as a priority queue. That is, here we should use only min heap as a priority queue. We should not go with maximum heap for Prim's algorithm. So min heap operation like extracting minimum element and decreasing key values takes order of log E time. So the overall time complexity for this Prim's algorithm is order of edges plus V, that is E plus V into order of log V time. So if we add together order of E plus V is common, so V into log V. So we get order of E log V as the time complexity analysis for Prim's algorithm. So the concept behind the Prim's algorithm is we are going to find a minimum cost by using minimum spanning tree algorithm. So in this minimum spanning tree algorithm, this Prim's algorithm, uh, the time complexity is order of E log.